Welcome to Astronomy State of the Art. This is a live session in our MOOC where the enrollment is actually about to hit 20,000. It's kind of an amazing number. So I know all of you aren't online, but for those who are, I'm ready to answer questions on astronomy. There's been a lot of astronomy in the news lately, a lot of things happening, so go ahead and fire up your questions.
Okay, the first question is from Zachary, and Zachary says, he asks, what is the primary objective of the James Webb Space Telescope, and is it going to unlock what really happened in the first few seconds of the universe?
So James Webb Space Telescope, it doesn't have one science mission, but its sort of killer app, if you like, or its big hook is first light in the universe. That's sort of what it was sold on. Now, in the end, you can't sell a huge mission like that, which is going to cost just as much as Hubble Space Telescope, without it doing a lot of science in a lot of areas. But James Webb, by being more of a near-infrared telescope than an optical telescope like Hubble, is perfectly tuned, and by having a much larger collecting area than Hubble, with a 6.5 meter mirror as opposed to a 2.2 meter mirror, 10 times more gathering power, is really designed to capture light from the very faintest and very oldest galaxies. The current redshift record for galaxies is about 8 or 9, which means their light is stretched by a factor of 10 in traveling to us through an expanding universe. And that means a light which was originally visible light, based on the sum of lots of stars, has shifted well into the near infrared. So when you look at galaxies that far away and that far back in time, they sort of stop being visible light objects. They become near infrared objects. So a telescope like Hubble simply can't detect them, for the reasons of that it's mostly an optical telescope with its best sensitivity, and it's not big enough. James Webb super overcomes those limitations in both ways. So the goal is to find the first light in the universe and ask some profound questions beyond when did the first galaxies form. Also, were the first objects in the universe stars or galaxies? There's not actually any evidence, although there's theory, on how the first structures in the universe formed. Some people believe, based on theory, that the first structures in the universe were actually stars, really massive stars that left behind a froth of black holes and exploded as supernovae and generated the first heavy elements in the history of the universe. Other people believe that the first structures to form by gravity were somewhat larger, like the size of dwarf galaxies, and then within those structures, stars formed. So black holes and galaxies undoubtedly formed coincident in contemporaneous time frame in the early universe, and James Webb is going to untangle that story, we hope. That's not, of course, all that James Webb is designed for. Because of the incredible progress in exoplanets, it's been used, it's going to be used for a lot of exoplanet work, and particularly for detecting exoplanets by their infrared radiation. Again, exoplanets are cooler than the stars they orbit, and so they put most of their radiation out. Their reflected radiation is infrared radiation. And the contrast of an exoplanet with a star is 10 or 20 times better in the infrared than it is at visible wavelengths. So exoplanet research is another area where James Webb is going to contribute. And there are many other aspects of science that it will contribute to, but probably those two are going to be the most common.
Okay, the next question is from Dragos, and the question is regarding new ways of measuring distances between galaxies developed at Keck Observatory. What is the science behind this Eye of Sauron?
No, that's interesting. I'm not up on the reference here, so you've sort of stumped me with your question. Matthew, do you know the Eye of Sauron? I'm not sure of the reference.
I think I can help out here.
Go ahead.
It's in Lord of the Rings, the Tower of Barad-dûr, the all-seeing eye that the Dark Lord Sauron would view is Middle Earth through. So it's his presence or his essence. It's kind of like an omniscient being.
Okay.
And so then the reference there, I guess they've been measuring the distance to a galaxy known as the Eye of Sauron, and they're developing new techniques around measuring galaxies to distance, distant galaxies.
Right. So I'm outed as not being a Lord of the Rings fan, I guess. So Keck is, of course, still one of the largest telescopes in the world, especially when the two 10 meters are working in harness with the sum of the 10-meter apertures. And they indeed are, you know, given the previous question about James Webb and Hubble also, you know, Keck is also preeminent in measuring the redshift of the most distant galaxies. So I'm not familiar with this particular galaxy with that Lord of the Rings reference, but in general, what the Keck Observatory is able to do is it's able to measure, to really push the envelope of measuring the redshift of faint galaxies. And when they're faint, they are far away, and so most of their spectral features, we're talking about the spectroscopy technique, are shifted into the near infrared. And you actually, so the state of the art there involves essentially cheating the atmosphere, because once you move into the near infrared part of the spectrum, the atmosphere is kind of dirty. It has a lot of absorption bands due to the molecules that the atmosphere is made of, due to the oxygen, due to the ozone, due to carbon dioxide, some carbon monoxide, even some methane. That's essentially all the molecules in the Earth's atmosphere, and most particularly the water, imprint complex absorption bands when you take a spectrum of the atmosphere. So you're having to detect really faint galaxy features superimposed on an ugly varying background of absorption from the atmosphere. And the Keck Observatory, not uniquely, but at sort of state of the art, has developed spectrographs that can do rock steady spectroscopy defining wavelength and differential spectroscopy to subtract out this signal from the sky. Now the signal from the sky, the absorption of the sky from those molecules, it also varies with time. And so you have to do this continuously. You have to do it in real time, because if you just average for a long period of time, you won't get a good result. So this is a technique that Keck Observatory uses to essentially dig out exceptionally faint galaxy spectra from an ugly background of absorption from the Earth's atmosphere. Now that background of absorption, of course, goes away if you're in space, hence the reason for telescopes in space. But again, Keck, we have no telescope approaching Keck in size, or the LBT here in Arizona. So for sheer light gathering power, you're always going to do better on the ground than in space. But for the stability of spectroscopy, the space environment is superior.
All right, the next question is about the Higgs boson. Stephen Hawking is warning that the Higgs particle could one day be responsible for the destruction of the known universe due to a quantum fluctuation creating a vacuum bubble that will expand through space, thereby wiping out the universe. Can you expand on this?
I don't know, but it's certainly got me scared just thinking about it. So Stephen Hawking is a brilliant man, of course, and you know, he raises alarms over various things. And I think it's always worth remembering with Hawking that he probably has one of the best and most impish senses of humor amongst all preeminent scientists. So, you know, sometimes what he says is deliberately mischievous or designed to be more humorous than serious. He's alluding to something serious, though. The Higgs particle, the Higgs is not really a particle. Most physicists don't talk about the Higgs as a particle. They talk about it as a field, which is a little more abstract and a little harder to understand. So people are familiar with the idea of an electromagnetic field, which can permeate space, or fields tend to be more dispersed and distributed than a particle, which is localized in space. And the Higgs phenomena is really the phenomena of a field. So we imagine the Higgs field permeating space and interactions of the things that we call particles with the Higgs field ascribe mass to them or give them mass. In this sense, you can think of it as the viscosity or the friction or the inertia of the things we call particles with respect to the Higgs field. The larger the amount of inertia or viscosity or friction, these are not exact physical words, but they're analogous physical words, the higher the mass of the particle. So that's what the Higgs phenomenon is. It ascribes mass to the things we call particles and explains why they have mass at all. Now, the question then becomes, what is the Higgs field fundamentally? And really, at that point, we don't know. The Higgs field could be associated with energy that comes from the vacuum, because indeed it is in the vacuum of space. If the Higgs field is giving mass to all particles in the universe, then it must permeate space, sort of in the same way that dark energy does, which is something different, we think. And what Hawking is sort of referring to is the fact that that any phenomena that can give rise to a field in the vacuum of space has the potential to create, vacuum bubbles or localized changes in energy. And if those vacuum bubbles or localized changes in energy have a particular property, then it's possible they can expand, and become visible and macroscopic. And I suppose in some version of the theory, these phenomena could take over the universe. It could be catastrophic bubbles or rifts in space-time emerging from a quantum fluctuation. So inasmuch as the Higgs field or phenomena is associated with vacuum fluctuations, vacuum energy fluctuations, then it's sort of related to this idea of vacuum energy bubbles coming and going in the universe, or possibly manifesting as expanding space-times that have disruptive properties. So it's all complete speculation. So I think just to ground all of this, we should just say that the Higgs phenomena is not fully understood. While the Higgs particle or field was detected convincingly a few years ago, the Higgs phenomena, its fundamental basis, is still not understood.
So the next question is from Stanley. How are the red and blue shifts of stars tugged by exoplanets measured with such accuracy given the incredible distance to the parent star?
Hey, that's a great question, because it's one of the most sensitive experimental techniques in science, in any field of science, let alone in astronomy. So it's a differential technique because you don't actually care about what the mean velocity of the star and the planet are. You're looking for the shift in the velocity of the star caused by the planet tugging it over an orbital period. So that variation can be quite sensitively measured. You guys, it's slightly hard to concentrate with that. So we're looking at a very sensitive differential technique. And the precision can be stated in terms of fractions of the speed of light. So a Doppler shift is basically a wavelength shift relative to the mean wavelength of the radiation being observed. And that, formally in the math, equals the velocity, the Doppler velocity of the moving object divided by the speed of light. The most precise versions of the Doppler method have precisions of 1 part in 100 million. In other words, if you had a Doppler shift, then relative to the speed of light, which is 300,000 kilometers per second, that's 300 million meters per second, then you're able to detect a few meters per second motion. And that's what the Doppler shift is able to do. And in fact, people think they can push the technique maybe a factor of 3 or 5 or possibly 10 below that to 1 part in a billion. So as far as the precision of the technique, it's 1 part in 100 million and potentially as good as 1 part in a billion. And what that manifests in is if you're measuring your wavelength, the mean wavelength of a feature in your spectrum, which would be something like 5,000 angstroms. An angstrom is 10 to the minus 10 meters, so 5,000 angstroms is somewhere in the orange-red range. You can actually measure a shift of that feature to 100 millionth of 5,000 angstroms, which is obviously something like a millionth of an angstrom. It's just a phenomenally accurate method. And to answer the last part of the question of how do you actually do that, that's the precision, which is really amazing. How do you actually do that? The way you do that is by having an exquisitely accurate wavelength reference for your measurement. So you need a reference frame or reference of wavelength. And that's done by putting a cell, a gas cell, in the light path of the telescope. It's either iodine or neon. It's usually an inert or a rare gas. And the light from the sky, from the astronomical object, passes through that cell, and that cell imprints a sort of a set of very narrow features, line features, onto the spectrum. So you get a reference grid of lines from the gas in the cell. And since it's on the same light path as your astronomical object, it's a perfect reference imposed on the spectrum you're trying to measure. And that grid of fine lines is the reference that allows you to be able to calculate a shift over time that's 1 part in 10 to the 8.
The next question is also from Stanley. How far are we from being able to determine the atmospheres and environments of an exoplanet during a transit?
That a technique, very important technique, because it's a prototype, it's a proof of concept method for how we might actually find life elsewhere. So hugely important technique. That a proof of concept of that method's been done 4 and maybe 5 times now with the Hubble Space Telescope. So just to be clear about the method, it's a good high-level question, but I should back off and say what the method is. So we have transiting exoplanets, and typically the transit is just used to measure the size of the planet. So the depth of the eclipse or the transit is a reflection of the relative size of the exoplanet to the star that it's crossing. So for a Jupiter crossing a star like the Sun, the transit is a 1% eclipse. The light drops by 1%. And for an Earth crossing the Sun, it's 100%, because Earth is 10 times smaller than Jupiter. So that's the transit itself. And we know from Kepler, with just a 1-meter telescope, that detecting a 1 part in 10,000 or 0.01% transit is not that hard. Kepler has done that routinely hundreds of times. The method that the question is asking about is a lot more difficult and includes a lot more information. That's using the fact that when the transiting exoplanet crosses the face of the star and crosses the limb of the star, then in principle the starlight can filter through the atmosphere of the exoplanet. So the exoplanet is mostly rocks, presumably, and it has a thin sheath of atmosphere. The rocky part of the planet is just going to be blocking that starlight, but the limb, the edge of that exoplanet, is the atmosphere, and light can filter through that atmosphere and reach our telescope. So what will that do? Well, relative to the situation where the exoplanet's not in front of the star, it will imprint an extra little bit of absorption onto the star's spectrum from the atmosphere of the exoplanet. So that's the principle of this experiment. You take spectra of the planet, of the star that the planet is transiting, before and after the planet is in front of the star. And when the planet is in front of the star, you get a diminution of light from the blockage of light, but you also get an extra amount of absorption from light passing through the atmosphere of the star. Very clever method, and it's been used, and it's a differential method because you're subtracting the spectrum with the planet not transiting and the planet transiting. It has to be done from space. Nobody's figured out yet how to do this from the ground because the atmosphere varies too much. But from the stable space environment with Hubble Space Telescope, it's been done 5 times, I think, with gas giants, though. So the exoplanets that it's been tested on are not the kind of planets like Earth. They're not giant Earths, or they're not even giant Earths. They're certainly not Earth-like planets. They're more like Neptune or Uranus. And the gases that have been found that way are, not surprisingly, obviously helium, hydrogen, which is what the envelopes of giant planets are made. Water vapor has been detected that way, actually steam, because these are hot planets. Sodium has been detected that way, and potassium. And these are trace elements in giant planet atmospheres. But that's a proof of concept for how you might, with the same method, and hopefully a bigger telescope, detect oxygen, ozone, methane, and the ingredients that would indicate to us biology operating on that planet. So it's an indirect detection of biology based on the fact that biology can globally alter a planetary atmosphere, as it did for the Earth, putting the oxygen that we breathe into our atmosphere a couple of billion years ago.
Okay, next question asks, I've been reading about the Rosetta mission to land on a comet. Why are we interested in landing on a comet, and what have they found?
So Rosetta has had its, a roller coaster, if you followed the news of the last few weeks. Rosetta is a mission of the European Space Agency. People living in the United States sort of tend to forget that the Europeans have a robust and well-funded space program too. And Rosetta has been one of the striking successes of the European Space Agency in the last few years. So why would we even want to do the very difficult thing of reconnoitering or rendezvousing with a comet and then sampling its material? It's really because comets are going to tell us about a couple of important things. They're going to tell us about how the solar system formed, because comets that are making their first passages into the inner solar system represent primordial or almost pristine material left over from the formation of the Earth and the planets in the Sun 4.54 billion years ago. So when we sample that material, which is essentially unaltered because the comet spends most of its time far from the Sun in the deep freeze of space, it's just unaltered for all that length of time, that's the primordial composition of the solar system. So learning how and when the comets formed is telling us about how and when planets formed. The second thing is that comets, we believe, are the water carriers of the solar system. Asteroids can do some of this too, but we know comets have large concentrations of volatile gases that are in a frozen state. They're called volatiles in general by the cosmic chemists. And that includes water vapor, but not entirely. It can also be carbon dioxide in its frozen form, dry ice. It can be carbon monoxide. It can be other gases, which at frigid temperatures become liquids or solids. So comets have a lot of ice, water ice and carbon dioxide ice. And it's speculated that that's how inner planets, terrestrial planets like the Earth, Venus, and Mars, got their water early in the history of the solar system. It was deposited or brought by comets that had orbits that brought them into the inner solar system, and in fact crashed into these planets and deposited the water. So taking, measuring a comet is going to tell you a little bit about that story. There's a very particular reason why, because there are two forms of water. There's normal water and deuterated water. Deuterium is an isotope of hydrogen, and so you can form isotopic versions of water that have different concentrations in space and on the Earth. So if you want to tell the story of how the Earth's water got here, you have to be able to match this isotopic ratio to the extraterrestrial material. So it's a very good test of the hypothesis of where the water came from. So that's why we want to go to comets. They're really important water carriers and messengers from how the solar system formed. Rosetta was opportunistic, and they picked as a target a comet that had spent really most of its life in the outer solar system, but had its orbit changed not long ago, astronomically speaking, to bring it into the inner solar system. And so Rosetta was designed to rendezvous with the comet as it's heading towards the Sun and heating up. And Rosetta did that incredibly difficult thing of rendezvousing with the comet a couple of months ago, which had never been done. Remember, it's obviously moving at 25 to 28,000 miles an hour, and you have to find it in space, in the depths of space, track it, turn around, and with rockets track it perfectly in its orbit to your parallel, and then essentially dock with it using gravity. And all of that was done successfully. The part where it didn't all go according to plan was when the Philae lander was launched a week or so ago. And that's an incredibly difficult concept, because you're dropping a 200-pound lander onto an object that has incredibly low gravity. And so the analogy people said was that the Philae lander's local gravity from comet 4067P made it weigh as much as a piece of paper. So you're basically having a lander try and float onto a comet and stick by this very weak gravity. And so where things went wrong is that the thrusters did not work as planned for Philae to get it into this landing trajectory. And then probably more importantly, the grappling hooks that it had, which were designed to grab the comet's surface so that it didn't just bounce off because the gravity was so weak, they didn't work either. And so what happened was it did bounce off. And it didn't end up in its original and planned landing spot. When it finally settled, it was under the lee of a cliff, which sheltered its solar rays from so much of the sunlight that might have been available to it, that it had to just do its experiments with the batteries that it landed with, and that was the end of the story. So that was a bit of a failure. I mean, there were a couple of malfunctions, distinct pieces of the mission that led to it not being able to have an extended mission on the surface of the comet. And also, I think one or maybe two of the instruments on Philae did not work perfectly as advertised, including one that was supposed to dig into the comet and get material and sample it and put it into a little oven and see what it's made of. But those were bumps in the road in the overall success of the Rosetta the mission itself to reconnoiter the comet, the lander, which did do scientific experiments before it went into a deep freeze after batteries died, and its continuing mission, which of course is going to track the comet as it gets close to the sun, as all this volatile material boils off, essentially making a tail, as comets get when they get close to the sun. Rosetta is just going to be watching all this happen. So actually, some of the greatest excitement of the Rosetta mission lies ahead in the next few months as that comet heads towards the sun. So a pretty striking mission, actually, and something never before attempted.
Okay, next question is, have you seen the movie Interstellar? What did you think, and how accurate is the science?
Yes, I have seen it, and it's, the director, to Nolan, the director is, it's Inception, it's a lot of movies that I liked. Memento, I guess, was the first one he was known for. So, very smart, savvy directors of complex, thoughtful movies, often with science in them. I was a little, I'm giving it a solid B probably because I like the acting. The script was kind of, it sort of mashed up the science a little bit, even though Kipling was advising, and he's one of the ultimate gravity theorists based out of Caltech. Some of his advice on, okay, you probably don't want to go there with your plot line was not taken seriously. So it is a case where the science got mashed somewhat, and then maybe, I'm not going to express the judgment on the artistic aesthetic merits of it, but it wasn't my favorite movie of that, from that source in terms of the way it was put together, either in terms of plot or continuity. So, like I said, solid B. It's fun to see those kind of concepts played out in a movie at all. So I enjoyed it for that reason. And sometimes, when you're a scientist watching a movie, it's dangerous to get into that nitpicky fact-checking mode. Sometimes you just want to sit back and enjoy it. And I did find myself doing
that. They also would like to know what you thought about the exoplanets that were talked about and how that relates to the course.
Oh, so there were some very extreme, if you like, hypothetical exoplanets. And that was certainly bending reality in terms of the type of exoplanets that we've ever found. So the exoplanet concepts in Interstellar are not like anything that's in the inventory of 3,500 confirmed exoplanets we have. But they're not ridiculous. I mean, they're not physically impossible. They're not even maybe implausible, given the totality of space and time and all the. I mean, remember, we're projecting with Kepler to a census of planets that probably rivals the number of stars in the galaxy. So we're talking hundreds of billions of planets in just one galaxy. And their physical situations and natures are going to be wildly different. They're not all going to be the same or similar to each other. So in that sense, I would cut the movie quite a lot of slack because it was just very imaginative what they came up with.
That's actually the last question for today. We think we've had some technical difficulties, and so we're out today.
Okay, that's great. Well, we'll be doing this. We'll definitely tuck one in before Christmas again, try and keep it every few weeks. And so everyone, hope you keep watching the news for astronomy. There's a lot of stuff happening, and we'll be doing this again. Thank you.